Chapter 20, Many Electron Atoms, Section 20.4, the Variational Method. Here we propose a anti-symmetric wave function for the two electrons in helium. Psi of electron 1 and electron 2 is equal to 1 over square root of 2 times n squared times the exponential function of negative zeta R1, another exponential function of negative zeta R2, times the spin part of the wave function, which is alpha 1 beta 2 minus alpha 2 beta 1. Here n is the normalization function for the 1 electron function. Zeta is the effective nuclear charge. R1 and R2 specify the distance between the two electrons and the nucleus. The expression of this wave function indicates that these two electrons together have an alpha and beta spin by looking at this. The z component of the spin angular momentum of the two electrons together is 0. So we know there's plus 1/2 h bar and minus 1/2 h bar. So together it's 0. Now let's determine the value of zeta. One way, of course, is to do the experiment. We just need to measure the amount of energy to remove both electrons from the helium atom. And that amount is 2.9 atomic unit of energy. And then we can divide this 2.9 between these two electrons. So each electron has a negative 2.9 over 2, that amount of energy. And we can just approximately state that the energy of each electron is negative zeta squared over 2, assuming it's a hydrogenic electron. And then we set up negative zeta squared over 2 is equal to negative 2.9 over 2. Zeta is determined to be 1.7. So that's how we experimentally determine the value of zeta. How can we determine zeta without doing any experiments? Well, we resort to the variational theorem. It states that whatever trial wave function is used to estimate the expectation value of the energy of the system, the trial energy is always greater than the exact energy of the system. The trial energy comes from the postulate 4 over here when we use the trial wave function. So this is the expression of quantum mechanical postulate 4. On the bottom, we have the integral of the complex conjugate of the trial function times the trial function. On top, we have another integral, which is similar, but over here, instead of the wave function, we use h, the Hamiltonian, applied to that wave function instead. So if we have a trial function, we can determine the trial energy. And the variational theorem states that the trial energy is always greater than the exact energy. The lower the trial energy, the closer the trial function is to the exact wave function. So how can we solve for the exact wave function? Well, one way is to propose a trial function with parameters, and then we can simply minimize this trial energy by varying those parameters so that this trial function is minimized. And when this trial function is truly minimized, it's equal to the exact energy. Now the problem of solving the Schrodinger equation for this multi-electron system becomes minimizing the trial energy in terms of trial function. For the helium atom, we can minimize the trial energy by solving this equation. The first derivative of the trial energy for the helium atom with respect to zeta, which is a parameter, should be 0. So really we're trying to find the value of zeta that minimizes the trial energy. So we propose this trial function for the helium atom. We have normalization factors, exponential functions of zeta times r. Here and here for the 2 electrons, we have the spin part. Now we evaluate the trial energy. We use postulate 4 here. We plug in the trial function. You may ask, what happened to the spin part? Well, fortunately, you see the integral of the spin part on top and also on the bottom. And fortunately, this Hamiltonian does not change the spin function, so we have the same spin integral on top and on the bottom. They cancel. So again, this Hamiltonian does not make any change to the spin part. Therefore, the spin integrals on top and the spin integrals on the bottom are exactly same. They cancel. The normalization factors also cancel. So for the helium atom, we have the trial energy like this. Let's compare these two integrals on the bottom. It's mostly the wave function squared. On top, it's the wave function multiplied by, well, the Hamiltonian applied to the wave function. So this is the trial energy. We have one parameter, theta, in the expression of the trial energy. How do we minimize the trial energy? Well, at the minimum, the derivative with respect to zeta should be 0. So we just need to solve this equation. We take the first derivative of the trial energy with respect to zeta. We set the derivative to 0. We just need to solve this. Well, solving this is non-trivial because, well, these two integrals cannot be easily solved, especially the top one. If you look at this Hamiltonian, perhaps the kinetic energy part, the attraction part are fairly easy to solve or relatively easier to solve. But over here you have 1 over R12. In this R12, the coordinates of electron 1 and the coordinates of electron 2 are highly correlated. We cannot separate those variables. So we can solve the top integral numerically, I believe. The bottom integral, I think, is relatively easy because we just have exponential functions. And this d tau is dr1, d theta 1, d phi 1 multiplied by r1 squared sine theta 1. And also we have electron 2. So we have r2 squared sine theta 2, dr2, d theta 2, d phi 2. But still, it's solvable. The top is more difficult, especially when we evaluate the integral that involves 1 over the distance between the two electrons. But still, numerically, I think it's possible to express this in terms of zeta and then evaluate the first derivative of the trial energy with respect to zeta. We set it to 0, and theoretically we can solve that equation and get zeta equals 1.7. Practically, it takes, I think, a very long time to do this calculations. You need to either write a program or maybe you can use a Excel spreadsheet to estimate those integral values. The effective nuclear charge of each 1s electron then fills 1.7 effective nuclear charge in the helium atom based on this calculation. And similarly, we can propose a trial function in the determinantal form for the neon atom, but with more parameters. You need, for example, effective nuclear charge for the 1s electron, for the 2s electron, and also for the 2p electrons. But still, in principle, we can just set this to 0. The first derivative of the trial energy with respect to parameter 1, parameter 2, parameter 3, they should all be set to 0. And then we can solve for the values of zeta 1, zeta 2, zeta 3, etc. for the neon atom. For any other atoms, we can use the same strategy. It's just we might have many more parameters to be optimized. The variational theorem states that whatever trial function you propose to estimate the expectation value of the energy of the system, the trial energy is always greater than or equal to the exact energy of the system. This equal sign holds only if your trial function is exactly the exact wave function. Alright, over here, this is the expression of the trial energy given the trial function. On the bottom, it's the integral of the complex conjugate of the trial function times the trial function. On top, it's the integral of the complex conjugate of the trial function multiplied by the Hamiltonian operator applied to trial function. We can verify this theorem by looking at one specific example. The particle in the box example. We know the exact energy of the particle in the box problem. It should be n squared times h squared over 8ma squared. When n is 1, we get 1 squared h squared over 8ma squared. Alright, but now let's propose a trial function like this. The reason we propose this kind of trial function is because when x is 0, the trial wave function is 0. When x is equal to a, the trial wave function is also 0. So at least when we propose ax minus x squared, this wave function becomes 0 at the two boundaries. When x is 0 or when x equals a, this value is 0. The square root of 30 over a to the power of 5 is the normalization factor. We introduce this normalization factor to ensure the integral of the squared modulus of the trial function is 1. So now let's use this trial wave function to get the trial energy. Again, this is normalized already. So the bottom integral is just 1. The top integral over here, we have the wave function here. And then this is the kinetic energy operator applied to the wave function. Because the potential energy is 0, so we do not have to write that part. It's just the kinetic energy here. And we can, take the second derivative of this function, which is just -2. So I put -2 here. The wave function copied here. Also, we have the normalization factor squared. I put it here, and then we have negative h bar squared over 2m over here. We just need to integrate this part. This part is pretty easy. We just need to somehow integrate ax and x squared separately. They go here and here. What happens to the -2 here is this. We have -1/2. -1/2 times -2 is just 1. So that's why -2 disappears. -1/2 disappears. So we get this equation. We plug in the lower limit and upper limit. We get something here, and then we clean it up. We get this value. This value is h squared over ma squared multiplied by a number, 5 over 4 pi squared. And 5 over 4 pi squared is 0.12665. Well, it's greater than 0.125, and 0.125 is 1 over 8, which happens to be the exact energy of the particle when its quantum number is 1. So we proposed a trial function. We get the trial energy, and the trial energy is indeed greater than the exact energy over here. So this is just a numerical example that shows that the trial energy is always higher than the exact energy. So one strategy of solving the Schrodinger equation is this. we first propose a trial function that contains one or more parameters. And then using this trial function, we can determine the trial energy that contains one or more parameters. And then we need to minimize the trial energy with respect to those parameters. That means if we have, for example, 3 parameters, Z1, Z2, and Z3, we just need to set the first derivative of the trial energy with respect to Z1 to 0, with respect to Z2 equals 0, with respect to Z3 equals 0. We solve all those equations to obtain the optimal values for those parameters. Now over here, there's also an example. We propose a trial function. In the end, we see this trial function has a trial energy higher than the exact energy.